Hi, well, here we go again. So we just introduced Banach spaces as normed linear spaces that are complete in the induced metric, and now the first task will be to familiarize ourselves with quite a few examples, okay? So the first one I started last time, sequence spaces, small lp, with the p-norms that we discussed in the chapter on normed linear spaces. They turn out to be Banach spaces for any p between 1 and up to infinity, including infinity. Okay, that's very different from the Hilbert space scenario. There, this will only work out for p equals to 2, that we proved. For the other values of p, to show that they are not Hilbert spaces, you use the Jordan-von Neumann theorem. All right, but that aside, now here I already said, so in order to prove that these LP spaces are complete for p equal to 1 and strictly less away from infinity, you just copy paste the proof essentially from the p equals 2 situation, because there, in showing that that space is complete, we actually didn't use the inner product at all. We only relied on the norm, that is Minkowski's inequality, and that inequality you have for arbitrary p. All right, so this just carries over at once. Now we will do here the case p equals infinity, simply because there, instead of having sums, you have the suprema. That changes things a little bit, but actually, if you carefully analyze now what I'm going to write down, it's exactly the same argument as if you were to operate with the sum, so when p is equal to 1 or strictly less than infinity. All right, but anyways, let's do this now for p equals to infinity. So the strategy will be to follow the three-step process, taking a Cauchy sequence, first cooking up a possible limit candidate and showing that that candidate is in L infinity, and then proving convergence in the infinity norm. All right, good, let's do this. So for p equals infinity, pick a Cauchy sequence, say xn, in L infinity, and write again. Remember, our space is a sequence space. That means each element is a sequence. So if you look at a sequence of elements, then you have to introduce the double index notation by default. And write again xn as x and k from 1 infinity, which is an element in L infinity n. All right. Then for fixed k, natural number, the sequence, this is exactly how we did it for p equals to 2, x and k, so you run out the n but you fix the k. This is a sequence of scalars, so either real numbers or complex numbers depending on the field. It is Cauchy y since x and k minus x m k. So what you're going to do is you're going to optimize it over k. Just keep the n and the m as is. Yeah, but then by our notation, this is here precisely the infinity norm of xn minus xm. And that infinity norm gets arbitrarily small for large n and m because our chosen sequence is a Cauchy sequence in that space with that norm. All right? That's why this is a Cauchy sequence, and since our field, either real or complex numbers, is complete in the absolute value or complex modulus, we know that these limits x and k as n goes to infinity pointwise in k exists as n goes to infinity. As before in the p equals 2 case, that allows us to construct the following object. This is a sequence y that is formed out of those pointwise limits, but now k is allowed to run up all the way to infinity. That will be our candidate. Now we have to check that that candidate is actually in small l infinity, so that is a bounded sequence. Okay. Now construct this and note that, well, for any given epsilon, there exists capital N depending on epsilon positive such that xn minus xm in infinity norm becomes small whenever these indices are large, meaning when they exceed that capital N. Hence, for arbitrary k and n, we have, now comes that game of the triangle inequality again. So here this is just the ordinary triangle inequality. If you do this for the p away from infinity, you use Minkowski inequality. So what you do is you add and subtract a bunch of terms, xnk plus small xnk, and then comes the large capital Nk, and you add the capital Nk, okay? And then as before, you're gonna chop up that thing after the second term and after the fourth term. And if you chop it up, so in other words here and here, then for the middle term, you're gonna optimize over k, right? So you take the supremum over all the k's for the middle term, and that is precisely the L infinity norm of the difference with the x sub small n and x sub capital N, right? So you can do this, and you can do the same optimization for the last term. So normally you would have here an x n k, but then you take the suprema over all k. So let me erase this and just put here the infinity norm, right? Notice that this thing is of course finite, because your these elements x sub small n or x sub any index, those are elements in L infinity. So that last thing is finite for sure, all right? So we have this, then with x small n minus x capital N is less than epsilon for n above n, because it's Cauchy sequence, and that first term, that difference yk minus xnk, that of course goes to 0 as n goes to infinity. That's precisely how the yks are after all defined, right? So what happens here is this guy, as n goes to infinity, goes to 0. This is already small, yeah, and this is finite for any capital N, right? So that means on the right, as small n goes to infinity, you have a quantity which is bounded in any k, right? The k is that index here on the left. So yeah, but then this precisely means if it's bounded for any k and the bound is independent of k, then it means that, well, that sequence y is in small l of infinity, right? Small l infinity, all right? Let's write this down. Hence, for every, what I just said in words, for every k in n, we have that yk is less than or equal to epsilon plus x capital N infinity. So indeed, y is an element in L infinity. All right, having established just that, now it remains to show that the convergence is also in the L infinity norm, okay? And that is very much like that part that we just did. Finally, again, for any epsilon positive, choose capital N and epsilon, so that the same as before holds true. That is to say that the difference x small n minus x capital N in the infinity norm is small for sufficiently large indices small n and capital N. Then for arbitrary kn natural number with n bigger than this n, same trickery, yk minus xnk. You're going to shove in that term with the m, and then, well, let's write this down as this, like so. Then again, this you optimize over k, you get to this point, so that whole thing is less than or equal to epsilon plus yk minus xmk. And this guy here, this guy here, of course, what happens as m goes to infinity? Well, that's precisely how our limit yk was defined. So this goes to 0. Since the left-hand side is completely, this side here is completely independent of small m, this proves the convergence in L infinity norm, right? Because this inequality holds true for any k, right? For any small k. So then you optimize over it and you get that the convergence holds in L infinity, all right? So let's write this down. This shows that yk minus xnk is less than epsilon for every k in n, and so the desired convergence holds. And so y minus xn infinity less than epsilon for small n above capital N. All right, that is the end of it. So the convergence is in L infinity, and that's why that space with that norm is complete. Okay, good. Now let's move along. So now there will be several other examples. The next space is actually a new space that we haven't encountered before. So this is C with a 0 index and then n. This is the vector space of sequences of numbers in F that converge. That's why the subscript there, that converge to 0. Okay, so formally Z0n is all sequences in F such that they have a limit, and that limit is equal to 0. All right. So first one should check that this is indeed a vector space, but that is a consequence of the limit properties of sequences in the real number field or the complex number field, right? So it's closed under addition, scalar multiplication, and it's non-empty. So this is a vector space. That claim is true. Now let's turn it into a normed linear space. Well, you can probably already guess that this guy is a subspace of the bounded sequences, right? If a sequence converges to 0, that means it is a bounded sequence. So that's why it's natural that I now look at these p norms, but to get to the target or to the goal quickly, I will immediately jump to the infinity norm with the infinity norm, right? So the supremum, all right? Now, as it turns out, with that norm choice, Z0n infinity is a Banach space, all right? You can ask yourselves now, it's a good exercise, maybe I'll put it on the exercise sheets. So what happens if you equip Z0n with one of the other p norms? You know, p away from infinity. Is it still complete or not? Well, give it a thought. All right, so I will prove this now. It's a Banach space. So first off, here we will be able to go a bit quicker about it, because I already said in words this guy is a subspace of, well, L infinity with that norm, and I know that L infinity with that norm is complete. So the only thing that I have to show in order to establish that this guy right now is a Banach space, I have to show that it's closed, right? that is that fact from metric space module that in a complete metric space, a subset is complete if and only if it is closed. That's what I'm going to exploit here, right? So first off, Z0n is a subspace of the bounded sequences. This I explained in words why that is true. Of L infinity M, so it's non-empty. So non-empty subset closed under addition and scalar multiplication. That's fine. Subspace of this. Second, if xn is a sequence in Z0n and this guy is convergent, now I will prove that the limit has to be also in Z0, okay? It's a sequence, say xn minus y infinity goes to 0 as n tends to infinity, then, this is the claim now, then y is also in that space. Okay, so how to do this? Well, as usual, whenever you work in those sequence spaces and you look at sequences, then you have to use the double index notation. There's no way around it. Might be confusing, but that's just how it is. Right, where y as, say, yk, k1 infinity, and of course also xn you have to write in this fashion. Okay, then here's a little computation. So yk, I have to show that when k goes to infinity, this quantity goes to 0. Then I would be done, right? Because then it means that y is a sequence that converges to 0. So how to do this? Yeah, it's always the same trickery. Up front, you subtract and add quantities that you can control. And here this would be this one. So you subtract and add x and k. Now the first one you're going to optimize over, well, k. That's clear because you have control over this norm, right? So there's essentially no other choice. So this will be at most y minus xn infinity plus x and k. Okay, good. And this holds true for any indices k n in n. All right. But now let's become formal. But given epsilon positive, there exists capital N and epsilon, so that this infinity norm up there, y minus xn, becomes small for sufficiently large indices small n, and thus, so I have already control over this guy up here. And now, of course, the idea is, you see the left, it depends on k. So you want to fix k at the moment and you want to send n to infinity, right? You don't want to send k to infinity. That will mess up your logic. So you want to send n to infinity. After all, only for this guy you have control in n, right? Not in k, right? So, but what happens when you send n to infinity here? For this one, well, it goes to 0. And why is this? Yeah, but this is because of the choice of the xn, right? So let's write this down. And thus, since xn is an element in C naught n, right? So when k, that second index, goes to infinity, this guy goes to 0. So this second term there also goes to 0. Okay? So we have therefore yk goes to 0 as k goes to infinity. So in short, or in summary, C0n with the infinity norm is a closed subspace of the Banach space well, L infinity with the infinity norm, L infinity n with the infinity norm, and hence itself a Banach space, right? I explained it earlier. Good. That's the second example. Now let's do, we can do one more in the current video. So third example is a subspace of the one that we just looked, or a subspace of the one that we looked before. So Z with 2 zeros in the subscript. So this is the vector space of sequences of numbers in F that have all but finitely many zeros. Okay, or zero terms. Let's write it like this. That sounds better. Zero terms. Okay, so this will be Z0 n. So those will be sequences n1 infinity in F, such that most of the terms are zero. In fact, all but a finite number of them. For all but a finite number, maybe here, number of n. Okay, again, this is clearly a subspace of the previous Banach space that we discussed, namely the Banach space of sequences that converge to zero, right? If you have a sequence and all but a finite number of terms are zero, that guy, of course, will converge to zero, right? If you have an element in them, all right? So that's a subspace, and we will equip it with the same norm. So equip Z0, 0, n with the norm, the infinity norm. Then the claim is also that guy is a Banach space. Is a Banach space. So we will use the same logic. We will just take a sequence in there which is convergent, and we will show that the limit is, well, again, in that space, right? Same logic as in the previous example. Okay, so first, clearly, here are the subspace containments. Z0 n is a subspace of C0, n is a subspace of C0 n is a subspace of L infinity n. That's how they're nested. So is a subspace of Z0 n. So if we have a sequence in it is convergent, say, well, xn minus y infinity goes to 0 as n tends to infinity. Since the example in the previous space was a Banach space, then we know that the limit is at least in there, right? Then y, how do I write it with n, is in Z0 n, by the last example, by the last. Okay, the same was with the same logic we could have pulled in the previous example. So that limit is for sure gonna be a bounded sequence, right? But we didn't use it. So, but here I will. So there I have this, okay, and now I have to convince myself that that limit is actually, well, in not just in C0 but in C00n, right? So we're gonna use the same logic as before, double index notation. So xn, xnk, k1 into infinity, which is in Z00n. We can find capital N sufficiently large large so that, well, that all the terms of this sequence x and k, as k varies from 1 to infinity, that at some point they must be 0, right? Because that's what's written up there. All but a finite number of terms are 0. So you just have to push your index far out, and then you're guaranteed that after that you won't have any non-zero contributions, right? That x and k for all k exceeding that capital N. Okay, in turn, same trick, same triangle inequality as before. For any k exceeding that N, actually this example is easier, although the last one wasn't hard either. X and k plus yk minus x, yk minus x and k. So now if that k is bigger than n, well then this guy here is already 0 because I'm away from the non-zero terms. And well, that second one again you optimize over the k, so y minus x and infinity. Yeah, but that goes to 0 by the assumed convergence. Right, so and that's why this holds true for all k sufficiently large. And this means, of course, well, that then the yks for k exceeding capital N, they are going to be 0. And that's precisely what you wanted to know, right? So which shows that y is in Z0n, so Z0n a Banach space. Okay, all right, so that's that. There will be more examples now in the next video. So now, earlier I already said you can ask yourself what happens if you equip those spaces with norms different from the infinity norm. So that's precisely a question that I will address early on in the next video. After that, more examples. Then we will go to the continuous functions on the unit interval and also there investigate which one of those with the p norms are Banach spaces and which ones are not. Okay, I'll see you in the next video.